In this lesson, we'll talk about the response of AC circuits in the frequency domain for the series RC, RL, and RLC circuits. We'll begin with a basic RC circuit with an AC source, as shown. Here we have a 10-volt AC source, a resistance of 56 kiloohms, and a capacitance of 2.2 nanofarad. Let's solve for the voltage output across the resistor and across the capacitor. From Kirchhoff's voltage rules, we get the following equation. For the output voltage across the resistor on the left-hand side, from Kirchhoff's voltage rule and the voltage divider equation, we get the following equation for the output voltage across the resistor on the left side of the page and the output voltage across the capacitor on the right side of the page. The equations were rewritten such that the left-hand side of both equations is given by V out over V in. So we have for the voltage across the resistor, the expression R over the square root of R squared plus 1 over 2 pi FC R over square root of R squared plus 1 over 2 pi FC quantity squared, and for the voltage across the capacitor as equal to 1 over 2 pi FC divided by square root of R squared plus 1 over 2 pi FC squared. Now let's plot V out over V in as a function of the frequency in order to take a look at the frequency responses. Here is the result of graphing the output voltage normalized to the input voltage. Their ratio is called the gain. Unity means the output voltage is equal to the input voltage. VR is the blue line, and while VC is the orange line. VR, the blue line, corresponds to the output voltage across the resistor, while VC, the orange line, corresponds to the output voltage across the capacitor. What this means is that if you use the resistor as the output voltage, any input voltage you will use, any input voltage will be filtered out at low frequencies up until the cutoff frequency. It only allows the passage of signals at high frequencies. In contrast, if you use the capacitor as the output voltage, any input voltage will be filtered out at high frequencies, starting from the cutoff frequency. It only allows the passage of signals at low frequencies. Both configurations act as a filter. Taking the output across the resistor is a circuit configuration called the high-pass filter, and taking the input across the capacitor is a circuit configuration called the low-pass filter. If the square of the ratio of the output voltage to the input voltage is 1/2, then the cutoff frequency corresponds to 1 over square root of 2, or 0.7071, which is somewhere here, or 0.7071 of the ratio of the output voltage to the input voltage, which is around this line. We derive the cutoff frequency as shown. It is defined as the frequency corresponding to when both the resistance and the capacitive reactance are equal. Thus, equating them and rearranging them to solve for F, we have the following equation for the cutoff frequency: 1 over 2 pi RC. Engineers love to put such curves in terms of gain in units of dB and the gain is computed by taking the logarithm base 10 of the ratio of the output voltage to the input voltage and then multiplying it by 20. If the ratio of the output voltage to the input voltage is 1/2, then the gain, if the ratio of the output voltage to the input voltage is 1/2, then the gain is equal to minus 3 dB. The corresponding frequency to the minus 3 dB point is the cutoff frequency. In general, the equation to convert from ratio of output to input is 10 log base 10. However, since we are working with phasors, we use the square of V out over V in, which is why a factor of 2 is included in the equation. If we increase the range of the gain to the frequency, we see the slope of the frequency response curve is 20 dB per decade. 1 decade means an increase in 1 order of magnitude. That is, for example, from 10 to 100 or from 10 to the 4 to 10 to the 5. You can see that this type of plotting is easier to interpret since you only need to identify where the minus 3 dB is and verify if your gain plot is correct. The bandwidth is defined as the width of the frequency. The bandwidth is defined as the width of the frequency over which the signal is allowed to pass. It is determined from the cutoff frequency. The low-pass bandwidth is in this figure the same as the magnitude of the low-pass bandwidth is in this figure the same as the cutoff frequency, since the signal is allowed to pass from f equals 0 up to the cutoff frequency f sub c. The high-pass bandwidth in this example begins from the cutoff frequency and continues on to higher frequencies with seemingly no decrease in output. We can also graph the phase angle with respect to the frequency and take a look at its behavior. We see that for low frequencies, the phase angle is practically 90 degrees and goes down to 45 degrees at the cutoff frequency. It continues to decrease as the frequency is increased until it reaches zero phase angle at very high frequencies. If we take a look at the phasor diagram, we know that the capacitive reactance lags the resistance by 90 degrees regardless of the frequency. However, the magnitude of the capacitive reactance decreases as the frequency increases. So this is extremely large if the frequency is near zero, and as the frequency increases, the magnitude of this phasor also decreases. This is because the capacitive reactance is proportional to the inverse of the frequency. Thus, at lower frequencies, you have a large XC corresponding to large phase angles, and at higher frequencies, XC decreases corresponding to lower values for the phase angle. Now let's proceed to the series RL circuit with an AC source as shown. This circuit includes a resistance of 12 ohms and an inductance of 0.02 Henry. Let's solve for the voltage output across the resistor and across the inductor. From Kirchhoff's voltage rule, we get the following equations for the output voltage across the resistor and the output voltage across the capacitor. Again, we normalize the output voltage with respect to the input voltage and obtain the following expressions for the resistor voltage and for the capacitor voltage. Now let's plot V out over V in as a function of f in order to take a look at the frequency response. Here's the result of graphing the output voltage normalized to the input voltage. VR, the blue line, corresponds to the output voltage across the resistor, while VL, the orange line, corresponds to the output voltage across the inductor. What this means is that if you use the inductor as the output voltage, any input voltage you use will be filtered out at low frequencies. At low frequencies, up until the cutoff frequency. It only allows the passage of signals at low frequencies. It only allows the passage of signals at high frequencies. In contrast, if you use the resistor as the output voltage, any input voltage will be filtered out at high frequencies, starting from the cutoff frequency. It only allows the passage of signals at low frequencies. Again, both configurations act as a filter. In this case, the inductor acts as the low-pass filter. In this case, the inductor acts as the the resistor acts as the low-pass filter, while the inductor acts as the high-pass filter. We derive the cutoff frequency as follows. It is defined as the frequency corresponding to when both resistance and the inductive reactance are equal. Thus, equating them and rearranging them to solve for f, we have the following equation for the cutoff frequency. From this figure, we see that the curve satisfies the 20 dB per decade slope, and at minus 3 dB, the cutoff frequency, where R equals L, is 95 Hz. The low filter bandwidth of VR is also 95 Hz, while the high filter bandwidth of VL is infinite. If we take a look at the phase diagram, we know that the inductive reactance leads the resistance by 90 degrees. We know that the inductive reactance leads the resistance by 90 degrees, regardless of the frequency. However, the magnitude of the inductive reactance increases as the frequency increases. This is because the inductive reactance is proportional to the frequency. Thus, at lower frequencies, you have a small XL corresponding to small phase angles, and at higher frequencies, you have a large XL corresponding to higher phase angles. We now know that the combination of RC and RL in a circuit with an AC source has a frequency response. Now let's take a look at how the series RLC filter responds to variations in input frequencies. If we plot XR and XC as a function of f, we expect the following. If we plot XL and XC as a function of f, we expect the following curve. In the frequency, we expect the following curve. Since XC is inversely proportional to f, we have this 1 over f curve. And since XL is proportional to f, we have this linear curve. In the frequency region where XC is greater than XL, the circuit is predominantly capacitive. In the frequency where XL is greater than XC, the circuit is predominantly inductive. At a particular frequency where XC is equal to XL, the circuit is neither capacitive or inductive, nor inductive and purely resistive, since XC and XL cancels each other out. The phasor diagram would just be the phasor XR or VR along the real axis, and the phase angle would just be 0. This is the condition for resonance. We can then solve for the resonant frequency of the circuit by equating XC and XL with each other. Solving for f, we have 1 over 2 pi square root of LC. If we consider this example, we can easily solve for the resonant frequency of the circuit to be FR If we consider this example, we can easily solve for the resonant frequency of the circuit to be F sub R equals 24 kiloohms. Plotting XL and XC versus F, we get the following graph. The blue curve corresponds to the capacitive reactance. The red curve corresponds to the inductive reactance. This black curve corresponds to the resistance, while this magenta curve corresponds to the total impedance. Now let's try to see what is happening to the series RLC circuit. We can easily see that the capacitive reactance falls faster than the rise of the inductive reactance. At F equals 0, XL equals 0, and XC is infinite. In other words, the capacitive reactance has an infinite value, and therefore no current will be allowed to pass through. The total impedance is purely due to the capacitive reactance. As the frequency is slowly increased, XC still has a very large value, but XL also has a value even if it's small. The total impedance then decreases not only because XC decreases, but also because of the difference XL minus XC. This means that the current can flow through the circuit elements, slowly increases with frequency, and the voltage is also present across the circuit elements. It follows that VC is greater than VL at these frequencies. At the resonant frequency, At the resonant frequency, XC is equal to XL, and therefore Z is equal to XR, as you can see from the figure. The current and the voltages R is also maximum. The current and voltages are also maximum and entirely through and due. The current and the voltage is also maximum and entirely through and due to the resistor. And entirely through and due to the resistor. Above the resonant frequency, XL greater than XC, XL is greater than XC, so that the total impedance follows from XL and becomes linear as well. The current then slowly decreases. Let's take a closer look at what is happening to the current and to the voltages across each circuit element. Note that the current axis is the left y-axis and the voltage axis is the right y-axis. At low frequencies below the cutoff frequency, below the resonant frequency, the capacitor voltage dominates and is equal to V sub S. In this graph, the current corresponds to the black curve, magenta corresponds to the resistor voltage, the red curve corresponds to the inductor voltage, the blue curve corresponds to the capacitor voltage, and this green curve corresponds to the combination of VL and VC, that is VL minus VC. At low frequencies, the capacitor voltage dominates and is equal to Vs, or the source voltage. As the frequency increases, the voltage increases due to the increase in voltage of the inductor and the resistor voltages. At the resonant frequency, the voltage is maximum. As the frequency increases further, the capacitor and resistor voltages decreases with currents. On the other hand, the inductor voltage flattens out toward the value equal to the input voltage, or V sub S. If we now take a closer look at the resistor voltage and the voltage across both capacitor and inductor only, we have the following curves. Using our knowledge of the voltage divider and taking the voltage across the resistor, we have the magenta curve. We see that similar to the RL and RC circuits, the input signal is filtered out except at values between 2 points in the graph corresponding to the minus 3 dB. These 2 points are F1 equal to 23.1 kHz and F2 equals 24.9 kHz. Thus, all input signal is filtered out below F1 and above F2. Only the signal between F1 and F2 is allowed to pass through. The frequencies F1 and F2 are called the cutoff frequencies. This range of frequencies covering the cutoff frequency is called the bandwidth, or BW. The resistor is acting as a bandpass filter. We also characterize the resonant circuit in terms of its selectivity. Basically, the narrower the bandwidth, the greater the selectivity. In the figure above, the blue curve has the best selectivity due to the narrower bandwidth. The quality factor is another parameter that characterizes bandpass filters. It is defined as shown. It is related to the bandwidth as shown. Thus, the greater the quality factor, the smaller the bandwidth, the better a circuit is. If we now take the voltage output across the inductor and the capacitor, we then refer to the green curve in the figure. The region between the cutoff frequencies does not allow the passage of the The region between the cutoff frequencies does not allow the passage of the input signal. Below F1 and above F2, the input signal is allowed to pass. This type of filter is called the bandstop filter. The range of frequencies between F1 and F2 is called the stop band. This type of filter is also known as a band elimination filter, a band reject filter, or through its more common name, the notch filter. Finally, we take a look at the phase angle as a function of frequency. At the resonant frequency, we already know that the phase angle is 0, since the reactances cancel each other out and the impedance is just equal to the resistance. At low frequencies, Xc is greater than Xl, and thus is more capacitive. This means that the phase angle approaches negative 90 degrees as the frequency approaches 0. On the other hand, above the resonant frequency, XL is greater than XC and thus is more inductive. This means that the phase angle approaches positive 90 degrees as the frequency approaches infinity. In this lesson, we'll consider parallel RLC circuits and discuss how they can be applied as filters. We already know how to treat parallel circuits with AC sources by converting the impedances to admittances, the reactances to susceptances, and the resistance to conductance. We'll be using those concepts here in this lesson, so it's a good idea to go back and review those concepts before proceeding. The simplest and yet most common type of parallel circuit is called the tank circuit. It is composed of an inductor and a capacitor arranged parallel to each other as shown. It is called the tank circuit because energy is transferred and exchanged between the inductor and the capacitor with no loss, ideally. The exchange happens on alternate half cycles. When the capacitor charges, the inductor loses energy, and when the capacitor discharges, the inductor gains back the energy or energizes. As in the series circuit, the resonant frequency also has the same expression and occurs when the inductive reactance is equal to the capacitive reactance. When X sub L is equal to X sub C, the currents through the inductor and the capacitor are equal in magnitude. Since those two reactances are always out of phase with each other by 180 degrees, then at resonance, the total current is 0. Let's consider this circuit as an example. Furthermore, let's consider the ideal case and ignore the resistance for now. The admittance is given by the following equation, where G is equal to 1 over R, B sub L is equal to 1 over X sub L, and B sub C is equal to 1 over X sub C, and Y is equal to 1 over Z. Since we are ignoring R for now, we also ignore G so that the admittance is purely due to the susceptances. The main graph shows the impedance curve versus the frequency, and the inset shows the current response to the frequency. At low frequencies, below the resonant frequency, Xc, the capacitive reactance, is greater than the inductive reactance, so that most of the current passes through the inductor. The capacitive reactance. Okay. At low frequencies, below the resonant frequencies, the capacitive reactance is greater than the inductive reactance, so that most of the current passes through the inductor. At the resonant frequencies, the impedance is infinite. It follows that the total current is zero, since the currents are equal. At frequencies above the resonant frequency, the inductive reactance is greater than the capacitive reactance. Thus, most of the current passes through the capacitor. Now let's consider the non-ideal case when there is resistance due to the winding of the coil. In this example, R is equal to 20 ohms. Since the resistor and the inductor are in series, we can solve for the quality factor as shown. These equations assume no loading effect from the input resistance due to the source or an external load resistance. We can convert the non-ideal tank circuit to its parallel RLC equivalent using the following equations. From the equation, you can easily verify that when Q is equal to or greater than 10, the equivalent inductance is equal to the original inductance. Why did we need the conversion from the non-ideal tank circuit to the parallel RLC equation? In the parallel RLC equation, we have the ideal tank circuit in parallel with RP equivalent. We already know how to interpret the ideal tank circuit. At resonance, the impedance of the tank circuit is infinite. Thus, the total impedance. Why did we need the conversion from the non-ideal tank circuit to the parallel RLC circuit? In the parallel RLC equation, we have the ideal tank circuit in parallel with RPEQ. We already know how to interpret the ideal tank circuit. At resonance, the impedance of this tank circuit is infinite. Thus, the total impedance of the circuit is equal to the equivalent parallel resistance of RPEQ and the tank impedance. Since the tank impedance is infinite, the total impedance of the circuit is just equal to the expression above as derived previously. Notice that the tank circuit's inductive reactance change. Since the inductance changed by a factor of Q squared plus 1 over Q squared, what would happen to the resonant frequency then? In other words, what is the resonant frequency in the non-ideal tank circuit? The definition of resonance is when the inductive reactance is equal to the capacitive reactance. So since we are now solving for the inductive reactance, since we are now solving for the equivalent inductive reactance, we can rewrite the equation as so and derive the resonance frequency as shown. Notice that if Q is greater than or equal to 10, then we revert back to our original expression for the resonant frequency. Let's now investigate how the tank circuit can be used as a filter. To allow us to be able to graph the results, I use R equals 20 kiloohms, L equals 50 millihenry, and C equals 47 picofarad. This gives us a resonant frequency at 104 kiloohms. In this configuration, when the output voltage is taken across the tank circuit, the circuit acts as a bandpass filter. The circuit is enclosed inside the magenta rectangle, and the result of the simulation represented by the magenta solid line. When the output voltage is taken across the resistor, the circuit acts as a bandstop filter. The circuit is enclosed inside the blue rectangle, and the result of the simulation is represented by a blue solid line. In this case, the bandwidth is about 2 kiloohms. It's very useful to some applications. What would happen if we added other resistances, such as the internal resistance of the source, the winding resistance of the coil of the inductor, and the load resistance? We already know what to do with the winding resistance of the coil. We convert this portion of the circuit to a parallel RLC circuit and solve for the equivalent RP and the new equivalent inductor. This new RP equivalent is then parallel to the load resistance. We can then solve for its equivalent resistance. In the figure, In the figure, it is represented as Rp total. Rs and Rp total forms a resistor voltage divider. Thus, the tank series sees a reduced input voltage. This reduces the output voltage and consequently increases the bandwidth. Remember that to get L equivalent, L is multiplied by a factor of Q squared plus 1 over Q squared, and thus L equivalent is actually greater than L. This means that XL increases and the total impedance also increases. This implies that at both sides of the resonance frequency, where XL is present, the impedance increases as well, which means a reduced current and a reduced voltage. This consequently results to a larger bandwidth. One typical application is a tuned amplifier. An amplifier is any circuit or device that increases the input signal. All signals that are taken as input by the amplifier are increased, including noise. Thus, if you use a tank circuit, you can improve the selectivity and decrease the bandwidth. A variable capacitor is typically included to allow for the tuning over a range of input frequencies so that the desired frequency can be selected. One such application is in your radio. The signal carried by the electromagnetic waves are detected by your radio through the antenna. This signal is very weak and needs to be amplified. It also contains a lot of unwanted signal, which is why you need the tank circuit to act as the bandpass filter. When you dial the knob, you actually change the value of the capacitance in order to tune to the station you want to listen to. A slightly more complicated circuit employed by your radio receivers is this super heterodyne AM radio broadcast receiver. Let's say that you want to listen to a radio station at a frequency of 600 kHz. The radio station sends out that specific frequency uniquely assigned to it. The transmitted signal, that is, the music or whatever audio, is carried by this 600 kHz frequency as an envelope. In the figure, it is represented by the border lines enclosing the main signal. While the antenna acts as some sort of filter, it still receives a large range of electromagnetic frequencies. The tank circuit filters out all the unwanted signal but keeps the 600 kHz signal. In this configuration, you have two tank circuits in series, both operating at 600 kHz. Such dual series filter is called a second-order filter. It improves the selectivity by increasing the slope of the signal. For example, a first-order filter, such as those we have been studying, is a first-order filter. It has a slope of 20 decibels per decade in the gain plot. Adding a second filter makes it a second-order filter and increases the slope by twice as much to 40 decibels per decade. At the output of the second-order filter, the signal is delivered to the mixer, where a 455 kHz signal more than the frequency of the input signal is added. This is why you have a 1055 kHz signal, since 600 kHz plus 455 kHz is 1055. So you add the 1055 kHz signal to the 600 kHz signal. This is the local oscillator signal local to your device. The 600 kHz signal is essentially removed through a process called heterodyning or beating. The 455 kHz local signal is the standard intermediate frequency for all receivers. This is then further amplified and filtered out at the resonant frequency of 455 kHz. The 455 kHz is then removed by the audio detector, leaving only the envelope, which is your audio signal. It's finally further amplified and sent to your speakers. Another application of filters is your crossover network. This network uses filters to separate the audio frequency bands, creating the variety and richness of sounds that you hear coming out of a set of speakers. The woofer employs a low-pass filter. The tweeter employs a high-pass filter. The mid-range speaker employs a bandpass filter, producing the frequencies not covered by the woofer and the tweeter.